Since I am in engineering, I was going to talk about the nature of feedback in engineered systems. But in discussions with my wife, who is a biologist, she wouldn't let me get away with that. So I had to go ahead and talk about sort of the feedback in both natural and engineered systems. Thanks again for showing up. Again, I know it's a really good day out there. I appreciate you taking the time to listen to me share with you a little bit about some of the stuff that occupies my time. What I was hoping to do today is go through a few things. You know, the first and foremost, to explain this idea of feedback. I mean, it's an easy word to say, but there are a lot of places where it occurs where you may not think it occurs. There are a lot of subtleties associated with it. And it is something that really is, I say, ubiquitous in both the man-made, human-made activities as well as in the natural world. What I like to do then is show you, okay, after I introduce this basic concept, where do you find this in different natural settings? And then talk about where do we see this when we try and design and build engineered systems. And then talk about some finer points. In particular, you know, how things go wrong, okay, and what happens when things go wrong in our feedback systems. And then finish up with some questions. And if you have questions as we go, feel free to go ahead and lob those in. I'm happy to take them. So this talk, when I wrote it up, I geared it for sort of the senior high school student who's taken an AP physics class. So you've heard about Isaac Newton, and he gave us some basic laws of motion. Right? And a lot of those we know very, very well. An object in motion tends to stay in motion. Another one that he gave us was for every action, okay, there's going to be an equal and opposite reaction. Okay? And that's something that's very, very basic. Right? Something comes in, hits something, it exchanges momentum, keeps going. Right? Now, this is an excellent example of cause and effect. Okay? There is a cause, comes in, right, and produces some effect on, in this case, it's a PowerPoint object. It's just a block. Okay? But you could conceptualize it. This could be many, many other types of things. The important thing here, sort of conceptually, right, is that there's this linear relationship among different events that happen. I guess there's only two events here, so that should be between if there are any AP English people in the class. But there's this relationship where there's a cause and a downstream effect, okay, and it happens linearly. What do I mean by linearly here? Okay, these things can be repeated and cascaded. Okay, so cause, effect, and the effect, that first effect, okay, can become the causation to another system, which can then have this cascading kind of down the line effect, cause effect, cause effect, cause effect. Something happens. It's almost like dominoes, right? As they would tumble on down. Right? But what happens down here has no effect on what happens upstream. Okay? Again, much like the dominoes, what sort of tumbles down usually doesn't come back around to the starting point. And that's basically kind of this Newton's law, every action equal opposite reaction type of thing. Okay, so what's feedback? I call it Mom's law. Right? My mom would tell me, you know, what goes around comes around. Okay, so make sure you do well out there and treat other people well, because what goes around comes around. This says, the general idea of feedback is if I have some cause, right, it's going to have an effect on some system, just like we had before. And that effect becomes a causation to a second event, okay, which then becomes the causation to another event. And you can end up having this downstream event affecting what started the whole chain of events. So you've got this feedback path. Okay, I don't just move forward in my cause and effect. Right? Some of these effects actually come back and affect the initial cause, or become the effective cause upstream. Now, this looks pretty simple, okay? And you think, you know, again, what's the big deal, right? this is a very, very key and fundamental aspect of a wide variety of systems. I mean, that little cartoon there gets the idea. Right? It's not a linear cause and effect. It's a circular type of cause and effect. And what happens is, on that linear cause and effect, you shoot through it once. On the circular cause and effect, it can go round and around and around and around again and again and again and again and again. Okay, there really is no end to it. That is visually, conceptually, what feedback is. Okay. In Wikipedia terms, which has now sort of become the de facto standard for defining anything, it's this circular causal process whereby some part of a system's output, and systems here would be those little blocks, the rectangles, okay, is returned or fed back to the input. Right? The feeding is the arrows. And those could be different things. Those could be power flow through big old electric power lines. That could be water flow through tributaries or estuaries. That could be information flow along fiber optics. Okay, it's the flow of something that affects these systems. And that comes back and affects what started everything. Okay. Examples of the feedback can be found in most complex systems in engineering, architecture, economics, and biology. We're not going to talk economics right now, although you can think about some pretty darn bad cause and effect that has happened recently. We're going to focus mostly on engineering and biology. Actually, it's a pretty interesting feedback system if you think about just a simple one. The one that I usually use, not this catastrophic stuff that just happened, but the Fed and interest rates. For those of you here that pay attention to that, right, there's this cyclical system where the Fed adjusts the interest rates, and that affects the economic output, which that gets fed back into your economic indicators, and then that gets looked at by the Fed to figure out whether they're going to adjust the interest rates again. And it's this sort of cyclical process that operates on a yearly basis. The causality is important in these feedback systems. This is, again, getting to this nature of cause and effect. Causality, right? It means that the actions or the information flow only in one direction. A is going to affect B. Okay? B does not directly affect A. Information or actions do not flow backwards. They only flow in one direction. A to B, B affects C, and C can affect A. Right? So the way that B gets back at A is through C. Okay? I can't just reverse direction. This causality here is actually very, very important in our notion of feedback. Does that, so far, what feedback is pictorially, conceptually make sense? Okay, I have an effect, which turns into a cause, which turns into effect, which turns into a cause, which turns into effects, and eventually comes back to me. Let me start the cycle over. Okay, so if you understand sort of the basics, you might say, does it appear anywhere other than this PowerPoint presentation? I wouldn't be having a job if it didn't. Right? You're going to find feedback everywhere. First, let's look at the natural examples of feedback, because I think if you're not an engineer and you haven't worked in this area of feedback, it's easier to sort of start off a little closer to home to understand what we mean by a feedback system. Okay, so one of the places where I first ran into Kevin was over in the stinky old man's gym across Springfield there, Kenny gym. And Kenny doesn't have air conditioning in the summer because it breaks a lot. So it gets really hot in there. Okay? And when you're exercising, okay, and you get hot, well, when you exercise, what you're doing is your muscles are generating a fair bit of heat. I mean, you're doing energy exertion, okay? And our body likes to stay at, I have no idea what it is in Celsius or Kelvin, but 98.6 in Fahrenheit. Okay, that's our sweet spot. That's where we operate. Okay? When we go ahead and do a lot of running, lifting, jumping, and we got to get rid of extra heat that would go ahead, if I'm dumping heat into this system that I have here, and I want to keep it at 98.6, I got to get rid of that heat somehow. Okay? And the way that you do it, if everything is working right, is you sweat. Okay? And believe me, in July and Kenny, you're gonna sweat. What does sweating do? Well, this increases the rate at which heat leaves your body. Right? Because the water is a much more effective way to transport energy away through evaporation, right, than just if you were to try and radiate that heat out. You ever notice, like, you take a cool mist and you run it across, or even a mist at room temperature, run it across your arm, it feels cooler than just if you're putting air across, because you're able to take more energy away through sort of evaporative heat, evaporation and convection than you could just radiating it. Okay. Well, this is what we call regulation of our temperature, our body temperature, thermoregulation. It's a big feedback system. Right? This is one of the blocks here, and that's me, kind of dragging here. And I'm doing all sorts of exercise and activity. Right? Somehow, some way, my body temperature changes. My nerve cells are able to go ahead and pick up the changes in my body temperature. Okay? Run that back to some comparator somewhere that's running in my nervous system. Okay? And from that, send a command to sweat glands, which open up, okay, which cause more heat to get taken away from my skin, okay, which then affects my body temperature, okay, which then gets picked up by my nerve cells, okay, which then goes ahead and does this comparison and tells my sweat glands whether to open more or less, et cetera, et cetera, et cetera. And then you keep going through this cycle, okay, as long as, well, you're continuously going through that cycle. What happens when you stop exercising is these guys pick up that this has now come back, you know, there's no longer a threat, so your nerve cells say, hey, it's okay to turn off the sweat glands. The sweat glands turn off, and you go back to sort of the non-sweaty condition. Right? But this thermoregulation is you're constantly monitoring the output of one process, okay, using that to feed another process, which then feeds the original generator of that information. That's a very, very sort of simple physical one. Hopefully here everybody sweats at some point in time, so you'd understand that. Okay, here's another one that you would see. Slightly more complicated. I guess it depends on if you talk to a geologist or a biologist, which one is more complicated. But the water cycle. How many folks here have actually seen this in class before? I'm very disappointed in the Urbana school system then. You must have seen the water cycle at some point in time. Okay, all right. You know, my kid, you know, Magic School Bus, they even have one on the water cycle. This is something that's very, very important in our overall well-being. And the water cycle is this type of a feedback system. Okay? You store most of the water that we have on the planet in the oceans. Okay? Maybe in the polar caps, but that's a small percentage of the total amount that you got in the oceans. Okay? Then what you do, and it's stored in, that's why I say liquid form, you go ahead and transport that water through evaporation up into the atmosphere. Okay? That mechanism comes from the sun. It's stored in the upper atmosphere as clouds. After it cools, it condenses. Okay? And then once you accumulate enough, right, you can precipitate that water out through rain or snow. Okay? Lands on the ground or on mountains and becomes ice if it stores here, or it goes into streams. Okay? And then the streams and rivers, and these can be above ground rivers or underground rivers, run off and get to the ocean eventually. Okay? And then you start the cycle all over again. And this is one gigundous feedback system. Okay? I have my blocks, my little blocks here. And sorry, I switched block colors and patterns on you here. But here is my ocean. I take condensation evaporation, which sends the water up into the atmosphere. Okay? That water in the atmosphere, notice I don't have a reverse of evaporation that directly sends water from my atmosphere back into the ocean. Okay, it's got to go through this condensation process, cloud formation, into precipitation, and then back down. Okay, that unidirectional flow of information or actions. Okay. The atmosphere then, through precipitation, dumps it back onto the surface. Right? You get surface and groundwater runoff that then goes back into the ocean. That's a feedback process. Make sense? Any questions on that? Here's another one that is another sort of natural, readily describable feedback process. And it has to do with populations, competing populations. Typically, we'll call these as predator-prey interactions if we just have two sets of populations that we're working with. In this case, I've chosen rabbits and foxes. Okay, so you got a bunch of cute little bunny rabbits, and I guess it's cute depending on whether or not they come in and eat your stuff at night. Your plants and stuff. If you have a bunch of rabbits running around the place, and you got a couple foxes that are kind of strolling around, life's pretty easy for those foxes. It's almost like a McDonald's. You can just sort of drive through and grab a rabbit, and you don't have to work very hard, and nobody else is looking for the rabbits, so there's plenty to go around. So I get fat and happy. Okay, I don't have to expend a lot of energy foraging for food. I can use that energy for other fun types of activities like raising a family and having kids. And so what happens is the foxes multiply. You get a lot of foxes. Okay, the fox population shoots up. Okay, the bad news is that then there's more foxes around. So more foxes, you got to feed them all, and you end up eating all the rabbits. Okay, so you end up with lots and lots and lots of foxes, and now not so many rabbits. Okay, so that's not really good. Okay, because there's no food for the foxes. Okay, so then they die off. Okay, well, if there's not a whole lot of foxes around, okay, chasing after us rabbits, right, life gets a little bit easier for us rabbits, and we can do what rabbits do and breed like rabbits, and you end up with right back where we were with a bunch of rabbits and very few foxes. Okay, and then this cycle repeats itself. Okay, and that's a giant population feedback cycle. Okay. You can even, never mind what this is here. This is numbers in I forget if it's thousands or not, data that was taken off of some study that was done, where you can look at the populations of the prey, or the rabbits here, right? They spike up, and then the fox population starts to grow. Now notice, the rabbit population, foxes are bigger than rabbits, so it takes a lot of rabbits to feed a fox. So the rabbit populations are a little bit bigger than the fox populations. But yeah, the rabbit populations peak, and then, whoa, there are a lot of rabbits here, so it's easy for me. My population starts to go up. But as soon as my population gets pretty big, all of a sudden I'm eating all my rabbits, so that comes down. If that comes down, my fox population dies off. And I have this sort of periodicity, okay, where my predators, they're eating all the prey, so the prey die off, so the predators die off. If there are fewer predators, the prey increases, okay, which causes my predators, or my foxes here, to go ahead and expand their population. And you keep going round and round and round and round and round. If you were to actually graph out, instead of as a function of months here, if you were to graph out blue versus green, okay, so if I looked at the rabbits versus foxes on the same graph, right, if this is rabbits and this is foxes, you're going to end up with something that just cycles. Okay, it feeds back, and you're just trading off rabbits for foxes, rabbits for foxes. But that's a feedback cycle. Okay, does that make sense? Do you ever wonder, like, some populations go away, and you're like, whoa, where the heck did they go? Right? And after a while, whoa, they're back. Right? It's sort of part of this natural, and it gets much more complicated when you have multiplayers, right? Where you have rabbits and foxes and maybe coyotes and other things, squirrels, and maybe you get the idea. You get a whole food web. The last one I want to touch on in sort of the natural, I kind of have to give a shout out to a local boy done good, Edwin Krebs. How many people here have heard of the Kreb Cycle? Okay, how many people know he went to Urbana High School? How many people here are from Urbana High School? All right, then I guess it's okay. I was going to call you out. Urbana High School, class of 1936, and then he went to U of I, graduated in 1940, got the Nobel Prize in 1992, and is one of our more distinguished alumni. This is the Kreb Cycle, also called the citric acid cycle. I prefer the Kreb Cycle because then I can just say it's one of the U of I alumni, display my Alleyne pride. It is one of the 3 steps for converting oxygen to energy in biological systems. And it's very much a feedback system where you will go ahead and, from glycolysis, introduce elements into this cycle that then go ahead and convert oxygen here into energy down here into ATP. And it's very much a cyclical process. I'm actually going to not spend that much time on this just because I want to get to some of the other things. Hopefully I've shown you, like, in natural systems, everyday systems, even when you don't even think about it. Okay, there are this idea of feedback. Okay, something affects something else. It's all, again, it's what Mom said. Right? What goes around comes around. Right? Something affects something, which affects something else, which affects something else, which comes back and affects the thing that started it. Okay, that happens in nature. Does it happen when we design our own systems? Okay, absolutely. And where are you going to find this? Everywhere. Again, it is ubiquitous. Obviously, I'm biased because this is what I do, but still, if you don't believe me, it's everywhere. I bet you at least 80% of you have a toilet in your apartment or your home. How many people have ever had to fix a running toilet? Okay, so you lift up the lid, and what do you see? You see that big old black ball or brown ball that's sitting there, right, on a big rod, right? Well, the way the toilet works, here this is a top fill, but you can also fill from the bottom. Right? You start filling up and filling up and filling up. Okay, so the water in the toilet, in the tank, is my system. What happens is this float here, okay, monitors the output of the water by moving mechanically, okay, and that motion affects a valve, all right, in the tank, right, and that valve affects the flow into the tank, okay, and the flow into the tank affects how much stuff is in the tank, which affects the float that's in the tank, and the cycle goes around and around until you reach some steady state equilibrium point where the float's high enough to go ahead and shut off the valve completely. Does that make sense? Diagram. You've got your tank, right? And then you've got your float. The float affects a valve, right? And the valve affects the tank. So you've got this feedback cycle to it. And your homework assignment is you can go back and play with the float setting to try and change what the equilibrium point is. How do you do that? Anybody know? What do? You just go ahead and bend it? Yeah, you just bend that wire back and forth to go ahead and, depending on what you want, if you want a little flush or a big flush. See, it's everywhere, I tell you, right? This one I put in there for history buffs because it is one of the first really well-designed feedback systems. How many folks have ever heard of the Industrial Revolution? You took history. See, this is a very well-educated audience. I like this. All right, so the Industrial Revolution, if you have in your mind a picture of what the Industrial Revolution was like, usually you have like this Charles Dickens type of, sooty sky and factories humming and all that stuff. And a lot of that was true, okay? What made that Industrial Revolution possible is before that, if you wanted to have power to run a factory or to run a mill or whatever, you had to go ahead and use a river, right? And the river had to turn a water wheel, right? And that turning of the water wheel, I could cue off of that turning of the water wheel and run some mill to grind flour, grind corn, or run some belt to drive a machine that I was using to sharpen, I don't know, some implement or tool or something like that. The Industrial Revolution happened because you're able to go ahead and have power or energy wherever you wanted, and you didn't have to be tied to a river source. Okay? They figured out how to go ahead and take a big pot of water, they call it a boiler, and they go ahead and heat it up really, really hot. They boil all that steam off, right? And the steam, when it boils off, if you ever have a kettle, you hear that thing go ee once it's actually boiling, right? That steam coming off, it's at pretty high pressure, right? That pressurized steam, it's got a lot of energy in there. I can now capture that energy and use it to turn something, right? Just like that water wheel. Right? And now I can cue off of that turning device, right? And run all my factory equipment. Okay? And I'm not geographically constrained. Right? I can set it up anywhere. All I need is coal or wood to run my boiler. Right? That's the good news. The bad news is if you go ahead and have too much pressure that gets built up in your boiler, right, you can have really bad things happen. In particular, an explosion. Right? And that's usually bad. That shuts down your factory for a while. And this is back in the days before they had OSHA. And so sometimes people would just figure that they'd run it until it exploded, and then they'd build another one. What you needed was a way to regulate the pressure coming out of those boilers. Okay? One of the things you could do is you could try and have a relief valve, okay, which was a pressure relief valve, so you'd maintain some pressure in it. What this guy James Watt figured out is I could do you one better. I cannot not only control the pressure in that boiler. What I'm going to do is I'm going to control the work output, how much power I'm sucking off of that thing. Okay, so what I'm going to do is I'm going to go ahead and cue the output shaft of this big wheel. Think about it like the equivalent of a water wheel, right? That's running all the equipment in my factory. I'm going to cue off of that speed, right? And I'm going to take that speed, okay, and let's say this is the shaft. It's going to be cued to this device here, right? And this is like a little pantograph. What happens is these are weighted balls here, right? And as this thing spins, centrifugal force makes these balls want to fly out to the sides. Right? When these balls fly out to the sides, right, it lifts up this part here. When it lifts up this part here, what that does is it adjusts a damper that sets the amount of air that goes into your furnace, which then controls the amount of energy that you're putting into your water, which then will control the steam pressure. Okay? And that way, I'm able to regulate the amount of power coming out of my boiler. So now I've got a controllable energy-producing, power-producing device. Okay, that I can move around anywhere, even on a steamboat, right? Which is another thing that this helps because it helps transportation. Okay, and so now I have controllable steam power, and that set my industrial revolution. Here's a kind of a neat little trivial fact, much more so amongst engineers. Anybody, I don't know if you've ever heard the term going balls out. Right? When I was in college, I thought it meant something completely different. This is actually a term that arose in the, again, the power plant industry. When you're running as fast as you can, right? Those little balls on your flyball, governor is what it was called, they're as horizontal as they can get. Okay? You can't be running your system any faster than that. Okay? And that's where the term, if you've heard it, comes from, meaning you're going as hard as you can. You're going balls out. Your factory's humming at peak power production. Okay? See, I told you, it even enters the language of the sort of common language, is feedback. Another thing, in terms of engineered feedback systems, is an idea of a cruise control system. Okay? you're driving along, and you set your cruise control at 65. You shouldn't set it above 65, unless you're driving through Montana or some other state that has a 70 mile an hour. But you know, you go above the speed limit here. You'll go ahead and set your little push button thingy on the steering wheel. Right? What happens is the car's speed, right, affects a little device that's spinning in your wheels. That little device that's spinning in your wheels, it's a speed sensor. That sends a signal back to an electronic control unit, an engine control unit, that then controls the throttle position on your engine, okay? Which then, by controlling the throttle position on your engine, it controls how much power you're sending to your engine, which controls the speed out of your car, okay? Which then gets picked up by the wheels. Right? And for example, if you set this at 65 miles an hour, you're going up an overpass, and all of a sudden 3 miles an hour. Okay? Maybe there is a 2 mile an hour difference between what you would like to have. Let's say this is, I didn't talk about it that much here. This idea of injecting external signals into the feedback loop is a way of shifting around where I want that feedback loop to come to steady state, right? Where I want it to settle out. Okay? That's an additional thing I haven't talked about too much. I'm going to kind of gloss over on this. But if this is coming in here at 63, based on the velocity, my speed signal picks up that I'm doing at 63 miles an hour. I've got a 2 mile an hour difference. What the engine control unit says is increase my throttle angle by 0.1 degrees. Okay, so I go ahead and open up my throttle angle a little bit more, let more air into the intake manifold. I get a bigger boom per combustion, right? And so I end up increasing my speed a little bit by 0.5 degrees. Then this thing becomes 63.5. Okay, this thing becomes 1.5, right? The engine control unit says, oh, maybe I increase now by 0.07. Now I get up to, I increase my speed by 1.1, and I keep going back through this cycle again and again and again and again until I actually get to that 65 miles an hour. That's a feedback system, right? I'm comparing the output out here, right? And that affects what was my original input to that system. Another example is a home heating. Okay, I've got a furnace. The furnace heats the house, right? And my little I love these little Galileo thermometers, right? That changes the temperature of the house. It's supposed to indicate temperature change in the house. That temperature change in the house gets picked up by my thermostat. That thermostat tells my furnace whether to turn on or turn off. Okay, and if my furnace turns off, all of a sudden that affects the amount of heat or lack thereof into my house, which then affects the temperature to change, which gets picked up by the thermometer, a thermostat that tells my furnace whether to turn on and turn off. And this is going on all night. Okay, and every time you hear your furnace go and turn on and then shut off, on and off, that's this feedback cycle that's picking up the temperature in your house and figuring out, what action to take, whether to turn on. This notion of feedback, again, is going to be everywhere. All right, so hopefully I've convinced you that it's ubiquitous. It's everywhere, right? Both in natural systems and in engineered systems. I mean, the temperature control in this room is one big feedback system. Okay, so we need it, right? And in most cases, it works just fine. Right? The problem is what happens when things go wrong. Okay. Usually when things go wrong, that's never a good thing. Right? First, let's talk about natural systems. Well, actually, before I do that, any questions on what feedback systems are? Either engineered feedback systems or natural feedback systems, where you'd see them. It was that clear. Okay. In natural feedback systems, what happens is a part of the overall system is removed. One of those blocks or one of the communication channels to communicate an action or information flow is removed. Let's look at this predator-prey thing. Okay, suppose I take out one of the elements. Right? I'll take out, in this case, the predators because the bunnies are cuter than the foxes. So I'll get rid of the foxes. Okay, what happens? Well, My rabbits are there. Okay, and they got nobody to eat them. And assuming that they got all the food that they need, well, they do what rabbits do, and do. And all of a sudden, you're overrun with rabbits. Okay, and that's not a good thing. Right? Does this ever happen? Anybody know what a zebra mussel is? All right, are they good things or bad things? They're a pain. All right, that's a beach that's not sand. Okay, those are mussels. Zebra mussels, they're an invasive species. They have no regulatory mechanism to eat them. Introduced into our lake and river system. Okay, and because of that, they have nothing to check their growth. So they've exploded. Right? And they clog up sewers, they clog up waste exhaust, they destroy beaches, they wreck ecosystems. Okay? And on the good bad, it's a little bit more towards the bad side. Right? That's what happens in a natural when a feedback piece is broken. Okay? Things go out of whack, out of balance. You can also see it in some part of a biological system. If in a biological system, if a part of the system is removed or damaged, the overall organism suffers. If there was part of this Kreb cycle where you're not able to convert oxygen to energy efficiently, that would be in disease state of the organism, some type of genetic defect. Worst case scenario, you've got some type of disease and you die. Okay? Nature develops these feedback systems to keep us in balance, to keep the ecosystem in balance. You remove part of that, the ecosystem goes out of balance, and it gets destroyed. Okay. Man-made systems, okay, similarly, feedback, if you remove part of it, the system won't work very well. It will be broken. Okay. Here's a little tricky thing, or finer for systems. For man-made systems, right, actually, if you put systems together in feedback, and all the pieces are working correctly, you can still hook it up where overall the system itself doesn't work well. So there's a problem. System here, where I have system 1 that feeds into system 2 feeds into system 1. Let's go through two simple cases. The first case is where the gain around this loop, right? So if I start off here with some information, and I pass that through this system, and I come back out here, and I come back here, overall, what comes out here is a fraction of what went in. Right? We'll start off. Let's say I've got a value of 1 here when I go around this, when I'm starting off on this first trip around the loop. Okay? And if my total multiplication factor around that loop here is a half, right? The next time around that loop I've got a half. Okay? The next time around the loop I've got a half of a half, or a quarter, and then I've got an eighth. And you see it'll keep going on and on and on, and I'll have this geometric progression of 1, a half, a quarter, an eighth, and gradually it'll die off to some 0 value. Okay? That's all good. That's all good. That's in our feedback system. I could shift what I consider 0. I could shift my equilibrium point. Okay? Much like in the cruise control example. So I inject an external signal there, my 65 miles an hour, which is a shift away. That's what my 0 point is. So as I die down to 0, that means I'm actually converging to this desired external signal. Okay? So this is the good case. Right? The other case I can look at is if this gain around the loop is greater than 1. Let's say it's 2. Okay? The gain around the loop is 2. I start off here as 1. My next time around the loop, I've got 2. Next time around the loop, I've got 4, then 8. And you can see now I've got this geometric progression that starts off at 1, 2, 4, 8. And I've got this divergence. Okay? In engineered systems, that's bad. Okay? That's what we call an unstable system. Okay? We have to make sure that the information that gets passed around this loop is attenuated somehow to make sure that my feedback system is stable. Okay? I'll give you an example. Here's a very, very simple example. Okay? See if I can do this. If I'm standing here, two systems that work fine if I separate the two of them. As soon as I go ahead and close the loop in feedback, so what the output of one is the input to the other, I've created havoc. Okay? Incidentally, that kind of stuff is why I have a job, to make sure when you close things, close the loop on things, you interact, you make things interact in feedback, things don't go wrong. Because when things go wrong, they can go really, really, really wrong. A lot of folks in the audience wouldn't remember this, but back in the 80s, there was this little accident, big accident, called Chernobyl that we had over in the Soviet Union. What happened was the feedback system, right, that was supposed to regulate the amount of energy that was being output by the nuclear reactor broke. Let me put it that way. There was a part of the feedback system, right, that wasn't working properly. Feedback system means you got these rods, and you can go ahead and quench how much energy is coming out of your reaction by into something that quenches the reaction. And that limits the amount of energy that comes out. And that was doing sort of the wrong thing. Okay? That was a broken part of the feedback loop. And they ended up having a nuclear meltdown. Right? So on these feedback systems, you kind of got to be very, very careful. I'm not going to go into details on exactly how, because don't have time for that. But suffice it to say that we have to be very, very careful about how we do this in engineered systems. So what are the takeaways, as you leave here? Right? First thing is your mom's always right. Okay? Listen to her. Okay? In this case, what goes around does come around. Right? The second thing is this notion of what goes around comes around is everywhere. Okay? Either in natural systems, processes running inside your body right now, gene regulation networks, right? Those are very, very complicated feedback systems. Okay. Engineered systems, you step in your car and there's a feedback system that's trying to make sure your engine isn't spitting out nasty emissions. Okay, trying to keep your air-fuel ratio at a particular ratio so that you get clean stuff coming out your tailpipe and it plays well with your catalyst. You go into your house, even your oven, man. You set 350 degrees on your oven. Something has to monitor to see whether it's 350 degrees and determine whether to turn on or off the heater. Okay? There's this feedback interconnection. Even simple things that you wouldn't think would have some type of feedback do. And we're in this information age. Once we enter this information age, right, where it's relatively inexpensive to move information to connect different physical things, all of a sudden the complexity and the amount of interaction and feedback exploded. I hope I gave you an idea here that not only is it important to understand that there is this feedback that goes on, but it's also very, very important to understand how it works and what happens if we screw up part of it. Okay? In the natural world, if we screw up part of it, we can have sort of ecological things happen. In the engineered world, okay, if we screw up part of it, we can also have very, very bad things happen, from our products not working properly to pretty major disasters. Not to leave on a downer or anything like that. I mean, it's actually pretty cool. This is going to be a field that has been around for a while and will be around for a while. If any of you are interested in learning more, I'd be happy to talk with you about it. But at this point in time, I'll take any questions that we have. Thank you. I guess it's a really nice day outside, and everybody sort of wants to. Sure.
Can you explain what negative feedback is? We hear that. I've heard that term, but I don't know how would that fit in.
Okay. So there's different types of feedback. The smart-ass answer to negative feedback is you go to your boss and ask him for a raise, and he says, "Get the hell out of my office. You don't deserve it." That's pretty negative feedback. There are a couple of different types of feedback, and if folks have to go, that's fine. I understand. If I bring information around this loop here, right, what I can do is the information that comes back, right, I can put a particular sign on this piece of information that's coming back, right? So there's a negative, whatever the output was on here, the negative of the output of this gets fed into the input of this other system. And usually if you have negative feedback like that in engineered systems, that causes the overall system, let me pick some variable x that corresponds to this particular system, tends to be a nice stable system. If I have positive feedback, okay, this would be like my, if this overall loop gain was equal to 2 and this was 1, I'd get 1 coming out here, right? There would be no sign change on this, and that's when I get this divergence. Okay, so usually that negative feedback is there to promote the stability of the overall feedback system. Sorry. The question is, what would you use positive feedback for? Sometimes you can use positive feedback if you're trying to drive an instability, okay, or if you're trying to drive some type oscillator, like a phase lock. You're trying to drive an oscillator, you can use positive feedback in that case. Yeah. That would be like a specific engineered system where you'd use positive feedback. Now, there is also this notion of feedback outside the engineered and outside sort of the biological. If you start to deal with human interactions, and then you get into sociology and psychology, positive feedback and negative feedback have two completely different connotations. Again, there are ways to motivate people by telling them they've done a good job so that they'll actually go ahead and try and buy into you and keep doing more. You can try and motivate people by telling them they suck and they have to prove themselves, right, and jump over this bar that you've set here. Anybody that's been on a sports team, there are two different types of coaches that'll use positive feedback or negative feedback to go ahead and get somebody to excel. That has a very, very different connotation from here because people work differently than machines, right? That's not the type of thing that we're talking about with the driving an oscillator type of feedback. Yeah. But positive feedback, if you do it well in personal interaction, usually tends to have better long-term impacts they've found than negative feedback. So one of the question was, what happens when you have more than one feedback loop? Well, what happens when you have feedback loops nested within feedback loops, and then I've got this feedback loop where this output now goes off to some other feedback loop up here somewhere, and does it get complicated, and do you see that a lot? The answer is yes, you do see that a lot. It gets really, really complicated. One of the better examples that people may have sort of more firsthand experience with, if somebody's not a geneticist or a molecular biologist, then that won't make so much sense. One of the things you could throw up there is you could show up one of these gene regulatory networks, and it's just all over the place. It's ridiculous. All right? A little bit more sort of close to home is our electric power grid. Okay, the electric power grid is a series of power plants that are distributed around the country, right? And they share electricity, right? You can, if you've produced a little bit more electricity than you have the capability to use in your own local region, you can actually sell that someplace else. Okay, so depending on prices, electricity moves back and forth. So you've got this interconnected network of power generation, power transmission, right, and power usage nodes that run across the country. If one of those things goes down for whatever reason, right, all of a sudden you get this cascading effect. Where it's very easy to get this cascading effect where one subsystem is expecting to have power because they've guaranteed that if I pay this price, I'm going to get that power, right? So I can meet my demands. And all of a sudden that power is not there, Okay? Maybe I go ahead and suck power away from an adjacent one that wasn't expecting me to suck power away from it just so that I can meet my demands. And then they go and say, well, I got to get power from someplace else, right? And that someplace else sucks power away from the one that grabbed it in the first place. And what ends up happening? Blackout, power failure. The Eastern Seaboard back in the 90s where everything went out. Okay? That's what happens. You get a collapse of that system. And it happens very quickly. Yeah, I anticipate that would enter in to the discussion. I would have to say at this point in time, it's not as well understood because the time scale is so long. Okay? On a gene expression network, the time scale on the effects that you'd have is on the order of, you're doing an experiment in your lab, minutes or hours. Right? Here, a lot of these time scales for understanding how the behavior of these systems, the overall temperature of the Earth, it's on the time scale of millennia. Okay? And so what we're trying to do is backtrack and understand from previous data what's going on, causes. Right? But we don't have the ability to go in right now and individually turn a knob, right, or pull a lever, cause an effect, and understand for this particular chunk of the system, let me isolate it from everything else like I could do in a biological lab, and I can study this, and I can go ahead and pull knobs and turn levers and wait for a million years and see what the response was, right? And then say, okay, every single lever I pulled has no effect on this, okay? Or there's something else that's causing it, and I don't know. We don't have the ability to do that right now. That's why it's really, really hard to go ahead and express exactly how all the different interconnections or possible causes could be affecting this. Yeah, working on really long time scales like that, it's really hard. All you can do is sort of look backwards. For a cruise control system, I got the ability to go into my lab and play with the knobs and try and figure out what affects what. I don't have that with the Earth.
If folks have further questions, I'm sure Andrew would be happy to stay around for a few minutes. You're welcome to come down front and chat.
Thank you very much for coming. Thank you for coming. Thank you for coming.